This energy is then collected and measured or analyzed to provide information about the incident radiation. Expected radiation to be detected by the detector could be alpha or beta or gamma, and purpose of detector determined by the type of detector that should be used for a given application. So if you need, for example, to measure the contamination, you have to select specific type of detector. You need to measure the leakage from the X-ray machine, you need to select something else. So depend on the purpose, you select your detector. Nuclear medicine imaging is generally based on the detection of gamma ray emitted by radionuclide, which injected into a patient, usually made from many orders. Like nuclear medicine images are produced from very limited number of photons. This is very limited number of photons if we compare it with the CT and X-ray. The flux photon from the nuclear medicine radioisotope is very limited. Functional information is produced compared to the anatomical detail of the CT. So the apparently poor image quality is overcome by the nature of the information produced. We are talking here about the functional imaging in nuclear medicine if we compare it with the anatomical imaging in the CT and X-ray. So before discussing the different types of radiation detectors individually, we would like to outline some general properties that apply to all types, such as mode of operation, efficiency of detectors, and also I would like to discuss the energy resolution of the detector. So we start with the modes of detector operation. The first mode is called the pulse mode, detect individual photons or particles. Most of radiation detectors used in nuclear medicine are operated in a pulse mode. That is, they generate pulses of electrical charge that are counted to determine the number of radiation events detected. The amplitude of each individual pulse carries important information regarding the charge generated by particular radiation interaction in the detector. So if we examine a large number of such pulses, their amplitude will not be all the same. Variations may be due either to differences in the radiation energy of the incident photon or to fluctuations in the response of the detector to monoenergetic system. The quantity measured is usually charge because we are detecting here charges or pulses. So the unit here is the coulombs, which is the unit of the charge, coulomb, okay? So this is the first mode of detector, pulse mode, detect individual pulses. The second mode of detector operation is the current mode, measure average rates of photon flux. At very high event rates, we have huge flux of photons. Pulse mode operation becomes impractical or even impossible to detect individual. We have flux of photon now. We cannot take one by one. For example, in CT scanner, because the X-ray photons arrive at the detector at very high rates, individual pulses cannot be separated for each interacting X-ray photon and detect individual. Therefore, unlike nuclear medicine, detectors that operate in pulse mode, X-ray detectors operate in integrating current mode. Nuclear medicine pulse mode, X-ray and CT integrating current mode. That is, they produce an output current proportional to X-ray flux and bending on them. So they give current, not charge here. We're talking about the current. The quantity measured is typically a current, amperes, or coulomb per second, because we are talking about the flux rate, coulomb per second. Okay, so current mode, it's for X-ray, because we have huge flux of photons. The pulse mode in nuclear medicine because we have less flux and we can detect the individual. Start with the detector intrinsic efficiency as well. Radiation detector quality expressed in terms of efficiency or sensitivity, energy resolution, dead time, and also counting rate performance. And intrinsic efficiency or sensitivity of a detector is a measure of its ability to detect radiation and is defined as number of pulses recorded, the ratio between the number of pulses recorded to the number of radiation incident on the detector. Not all radiation incident on detector will be recorded or will be registered in the detector. So the ratio between the number of pulses recorded that hit the detector and also recorded, okay, to the number of radiation incident on the detector, the total number of radiation incident in the detector. So we get the efficiency of that detector. The efficiency range from 0 to 100% and depends on the type and energy of the radiation. It is alpha, it's beta or gamma or whatever, and what is the energy of the incident photon, and on the attenuation coefficient and the thickness of the detector receiving these photons. The higher the energy, the higher the efficiency of the detector, the better it is for use in nuclear medicine, because we need more count to detect. To get better image quality, to reduce the noise, we need more counts, okay? We need to enhance the efficiency. Better efficiency means better image quality. High intrinsic efficiency allowed a shortened imaging time, reduced radiation dose to the patient, or both of them. So if we have high count, we don't need to inject the patient more activity to get the counts. And also we can shorten the scan time because we have enough count. We don't need to keep the patient on the bed for longer time. Detector energy resolution, it is ability of detector to distinguish between two radiations of different energies. So if we expose a detector to a monoenergetic beam of gamma ray and plotted the distribution of measured photon energy, would obtain an energy spectrum similar to the one here shown in this graph. It's Gaussian distribution, similar to the Gaussian distribution. The energy resolution of a peak can express at the width of the peak. Thus, a good resolution means narrower peak width. So this is called a conventional way to define the width is the full width at half maximum. This is the full width at half maximum. The full width at half maximum defined as the width of the distribution at a level which is just half maximum ordinate of the peak. Okay, so this is the full width half maximum. We need narrow full width at half maximum to get better energy resolution. If we have wide full width half maximum, means that we have poor energy resolution and poor resolution in general. So we always look for the narrow full width at half maximum to say that the detector has the ability to distinguish between two different energies. Another parameter to discuss for detectors is dead time, is an important factor affecting the detector. It is a measure of the ability of a detector to function accurately at high count rate encountered when large amount of radioactivities are used. So for any detector, there is a small interval between the time when radiation interacts with the detector and the time when the detector responds and the event is recorded. So the minimum time separation is known as the time. So detector receive one event, now is busy recording this event. So if another event comes in between, so the detector will not accept this event because the detector is busy processing the first event. So this interval of time is called the time of detector. The detector is busy and cannot accept more events. So the detector is not responding. Okay, this interval of time called the time. Ideally, the detector should have as short a dead time as possible to detect high count rates without significant losses. In nuclear medicine, a system dead time of about 2 to 3 microseconds is acceptable. So these dead time losses can become rather severe when high counting rates are encountered, and some correction of these losses should be included to get an accurate measurement. So we cannot accept this dead time every time if it is severe. Let's go to radiation detector in nuclear medicine, or in general even. The first type of detectors, radiation detector, is gas field detector. Before that, anyone, any question so far? Okay. The first type of radiation detector is the gas field detector. The basic principle of the gas field detector that it is a volume of gas is combined it is contained between two electrodes having a voltage differences and thus electric field between them. So under the normal circumstances, the gas in an the gas here inside between the two electrodes are insulator and no electrical current flow between the electrodes. However, the radiation passing through the gas causes ionization. The electrons produced by ionization are attracted. The electron will be attracted by the anode here. The positive ion will be attracted by the cathode. So the incident radiation causes ionization. These ions attracted by the two electrodes, minus to positive, positive to minus. The ionized atom to the negative electrodes here, so we create the current one. The electrical charge liberated by ionizing radiation is collected by the positive and negative, and create some like what we call the current between the two electrodes. In gas field detector, the magnitude of the voltage between the electrode, the anode and the cathode, determine the type of response to incident photon. The gas field detector include ionization chamber, a proportional counter, and Geiger-Miller. However, the use of these detectors in nuclear medicine is somewhat limited because their stopping power and detection efficiency for X-ray and gamma ray are quite low. So we use them in survey meter and contamination monitor, but we don't use this kind of detector in nuclear medicine imaging. Before first region, there is one region here is called recombination region. So for maximum efficiency of operation, the voltage between the electrode, the anode, and the cathode must be sufficient to ensure complete collection of ions produced and electron by radiation within the chamber. So when the incident radiation passes through the gas, it produces ions. So the voltage should be adequate to collect these ions produced inside the gas. So if the voltage is too low, the applied voltage is too low, some of the ions and electrons simply recombine with one another without contributing to electrical current flow. So the output of the detector operated in this region would not representative of the incident radiation. So because the ions recombine together and we don't get an output. So in this region, the detector is not operated. Region 1 is called ionization region. So when voltage becomes sufficient to cause complete collection of all of the charge or primary ion pairs produced, the curve enters a plateau called the saturation region, means that all primary ion pairs produced by the radiation incident have been collected. Okay, this is the plateau here, the same one. This is so the voltage is adequate to collect the ions, and we reach to the that means that we reach to the plateau. The voltage at which the saturation region begins, called the saturation voltage, this is it's about 50 to 300 volt. This is the saturation voltage. The energy required by a single ionization radiation event to produce one ion pair is approximately 34 electron volt. So to produce one ion pair, you need at least 34 electron volt to produce one ion pair. Thus, if we have 1 million electron volt beta particle, this causes about 30,000 ionization in air and release a total amount of electrical charge of only approximately 3 to the power minus 15 coulomb. So this is the first region of the voltage. Apply between 50 to 300 voltage, we get the ionization chamber region. Most of the ion inside the gas will be collected by the electrodes, and we get the saturation region. Ionization chambers are operated at voltage in the saturation region, as we said. In this region, a small fluctuation in the applied voltage do not affect the output current significantly. So we say ionization chambers are stable. And we can see here is the applied voltage, okay, and here is the amplitude. So if we change the applied voltage here a little bit, so the output signal will not be affected, will still same. So this is considered the stable kind of detector, the ionization chamber. The ionization chamber generally is not used to count discrete radiation event. Instead, the average number of ionization per minute occurring within the gas is measured. That means ionization chamber is operated in count mode, not in the pulse mode. Because of the small amount of electrical charge or current involved, ionization chambers generally are not used to record or count individual radiation events. Instead, the total amount of this one, we say the current. So it is ionization chambers are quite inefficient as detector for X-ray and gamma ray. Only very small percentage, we talk about less than 1% of X-ray or gamma ray passing through the chamber actually interact with it and cause ionization of air molecules, and this is considered low detection efficiency. So application of ionization chamber in nuclear medicine, the first one is the radionuclide dose calibrator. National and international regulations require that every dose of radiopharmaceutical to be administered to patient must be measured prior to administration, and this achieved using a dose calibrator. Dose calibrator is a well-type ionization chamber used for measuring and verifying patient doses, or it also measure the generator elutes or shipment of radioactivity. If you need to ship radioactivity, everything you use in the nuclear medicine should be measured before used in the dose calibrator. Dose calibrator employs sealed and pressurized chamber filled with argon gas. This is the well, the hole. We put the sample inside this well, okay, and around this sample here, there's pressurized argon. The purpose of the argon inside this chamber is to eliminate the effect of changing barometric pressure on the output reading to keep the pressure inside the well. Those calibrators typically are calibrated to read directly in units of activity, either becquerel or curie, with a switch here set the display different radionuclide. Ionization chamber have no inherent ability of energy discrimination. What does it mean? So different radionuclide with the same amount of radioactivity produce different amount of current. So if I have same amount of activity of iodine-131 and same amount of activity of technetium-99, if I have 5 millicurie technetium-99 metastable and I have 5 millicurie iodine-131, and put them in the dose calibrator, I will have different reading. I will not have 5 millicurie for each one, because this dose calibrator cannot discriminate between the energy. So we need to calibrate the dose calibrator for each radionuclide. This calibration done in the manufacturing, and we follow that after we receive the dose calibrator in nuclear medicine. We just check every day the calibration factor that it is accurate and give us the accurate activity. For each radionuclide, we do the calibration to get the accurate activity. So the calibration factors. So, okay, I'll repeat that. The calibration factor for a number of radionuclide are created and stored, and the user should select the correct setting before measuring the dose, apply correct calibration factor. So if you go for technetium, there's a bottom. Say, okay, technetium, you just press on the bottom, technetium to select that. We said that ionization chamber cannot distinguish between different energy. So iodine-131 has energy 360 something. Technetium-99, the energy of the photon 140 keV. So different energy will be measured inside the dose calibrator. The interaction of photon of 140 keV is different than the interaction of the photon of 360 inside the dose calibrator. So the amount of ionization inside the ion chamber, which is the dose calibrator, will be different. Will be higher for iodine-131 because iodine-131 has higher energy, 360. So 360 will give different reading, different ionization will occur inside the gas, while the technetium also interacts with the gas, but in different way because different energy give different number of ionization. So the activity, the production, the signal will be different. And when we convert the signal to activity, also it is different. So we get different activity, we will not get accurate activity. So what they do, the manufacturer, they calibrate the iodine-131. They have reference dose, for example, 5 millicurie of iodine-131. They put it in dose calibrator. They change the calibration factor until they reach the 5 millicurie, and they then store the calibration factor for each radionuclide. When we receive the dose calibrator in nuclear medicine, we have bottom. We have calibration factor also. We have the number. So there's a bottom, and each bottom programmed for different radionuclide. You select the radionuclide before you measure. If you have iodine-131, you select the iodine-131 in the dose calibrator, then you measure that. Because different energy, different response, different reading. It's already calibrated in the manufacturer. That's why you need to select the proper radionuclide before measuring. Did you get that? Okay. The second application, thank you. The second application of ionization chamber is the survey meter. The survey meter is a portable ion chamber, are used as survey instrument for radiation monitoring purposes. Ionization current is displayed on a front panel meter. Many older units are calibrated to read a traditional unit of exposure rate in Röntgen per hours, or milliröntgen or Röntgen per hour, whatever. And newer units are calibrated to read system international unit for air karma in grays per hour. So it is easier for us to read if gray per hour or sievert per hour, because all the limits put in sievert per hour. For example, we need this area to be not exceed 1 millisievert per hour. We just bring our survey meter, measure, it is okay, save. So they give us direct reading, how many sievert per hour we get, the effective dose rate, we can get it immediately by using this kind of survey meter. The current reading is, the low sensitivity ionization chamber, low different voltage between anode and cathode. So it has, so this kind of survey meter has low sensitivity, okay? So used with high flux X-ray and gamma ray. So this kind of survey meter cannot be used for contamination, to detect contamination. If you have radionuclide on the surface, you have contamination, it is not recommended to use the ion chamber survey meter to detect that, because the efficiency of the ion chamber is very low. It will not detect very low activity. It might be contamination on the surface, but the survey meter cannot detect it. Okay, we'll come to another kind of survey meter can detect the contamination. Okay, any question about ionization chamber? So we are still in the gas field detector. The second region, the operating voltage region, is called a proportional region. In this region, voltage is increased to a sufficiently high value, and the electrons liberated by the radiation are accelerated toward the positive electrode and cause additional ionization in collision with other atoms in gas. So we can see here the regarding the question here, yes, we have calibration factor for each radionuclide used in nuclear medicine. Okay, let's go back to this one, gas field detector. So the ionization particle passes through the gas, it creates ion, we said, electron and positive ion. The electron is going to the anode, interact with another atoms inside the gas, and they produce another ions. And the electron produced from this ion will produce another ionization. So this is kind of cascade process called the Townsend avalanche. And the ionization multiplication factor is called the gas amplification factor. So the electron, the primary electron, produce ionization. The incident radiation produce ions. The ions, like we have positive ion, we have electrons. The electron produce more ions, and another electron here, it produce more ions, and this is kind of cascade, continuous cascade, and this kind of amplification, and each kind of detector has a amplification factor, non-amplification factor. Okay, the total charge produced equals the number of ionization multiplied by the gas amplification factor. We know that to produce one ion pair, you need at least photon with 34 electron volt to produce ionization or to produce ion pair. Okay, so the total charge produced inside the detector is the number ionization multiplied by the gas amplification factor for each detector. Therefore, number of electrons in the overall signal is proportional to the energy of the incident radiation. So this is like related to radiation, the incident radiation. This is the region of the proportional counter. So the major advantage of a proportional counter versus ionization chamber is that the size of the electrical signal produced by an individual ionizing radiation event is much larger. Also, because the size of an individual pulse is proportional to the amount of energy deposited, the proportional counter can be used to discriminate between radiation events of different energies. Okay? However, this kind of detector has poor efficiency, so very limited in nuclear medicine. This kind of detector mainly used in research involving non-penetrating radiation like alpha and beta emitter. So we don't use this one in a clinical anyway. A proportional counter, you find it maybe in the university, in kind of research to detect the charged particle. Okay, but the advantage of this kind of counter, it discriminates between the energy. Okay. The third region of gas field detector here is called the Geiger-Müller region. In this region, the operated voltage are so high. We are talking about 900 to 1200. So the free electrons primarily and secondary electron are accelerated to very high speed. So when excited electrons, so this is the incident photon here. When excited electrons return to the ground state, the ultraviolet photon produced can induce additional ionization, which can trigger additional cascades. So this is the incident radiation. It produces ions, electrons, and again, positive ion, okay? So some of the electrons will go for excitation state, okay? Go to upper state, then go down again to its ground state. When this electron go back to its ground state, emit ultraviolet radiation. These ultraviolet radiation interact with the atom of the gas and produce another ionization. And these ionization produce another ionization. This is kind of cascade, continuous cascade. This process is terminated when a sufficient number of slow-moving positive ions collected around the anode, effectively reducing the electrical field below the level required for gas multiplication. Okay, so this is the anode here. When we have very slow, because the protection is very high, the ultraviolet produce another ionization produce ultraviolet, and so on. Ionization is continuous. After sometimes around the anode, they collect very slow, heavy positive charge. So this reduces the electrical current between the cathode and anode, and by this way, this cascade, this cascade or the continuous ionization process will be terminated in the Geiger mirror counter produce a very large signal. You can see here, this is the signal, this is the output voltage. You can see it's higher than a proportional counter, it's higher than ionization chamber. Signals are independent of the incident radiation energy. So this kind of detector cannot discriminate between the energy. Geiger mirror counter are more sensitive than ionization chamber survey meters. Geiger mirror counter can be used to detect and count individual ionizing radiation event, so it's operated in pulse mode. However, because the size of the electrical signal output is constant, you see here plateau. Regardless of the energy of the radiation detected, a Geiger mirror counter cannot be used to distinguish between radiation events of different energy. We say that kind of Geiger mirror counter cannot discriminate between different energy. Okay, so Geiger mirror counter is good for contamination monitor. Providing radionuclide identity is known. So Geiger, if there's any contamination, Geiger mirror can detect this kind of contamination. They say, okay, there is contamination, but we don't know what kind of contamination, because this kind of detector cannot distinguish between the energy. So it gives us signal that there is contamination. There is some activity on the surface here. But if we want to know what kind of contamination, we cannot know by using the Geiger mirror. We have to use different detector to discriminate between the energy. Could be scintillation detector or other type of detector. Semiconductor detector can distinguish between, okay, this give energy 360, for example, okay, this is iodine 131. But with Geiger mirror cannot distinguish the energy, cannot identify the radionuclide, only detect that there is contamination on the surface. The last region after the Geiger mirror, the gas in this chamber can undergo spontaneous ionization due to the energy provided by the high voltage across the electron. So if we keep increasing the operating voltage to very high, what happened here? In this region, no useful information can be gained. So detectors are not operated at this voltage. It can be even shorten the life. Okay, in this region, a very high voltage. So we get signal, even without radiation, we are getting signal because the high voltage applied in this kind of detector, okay, we get signal. It's create ionization in somehow, and we get output signal, and it's not related to any incident radiation or detection in radiation. So we keep getting the reading, and we don't have any kind of radiation. So it is not reliable region. So in this region, the detector is not operated. To summarize that, gas field detector detect ionization produced by radiation in gas. Ionization chambers, a proportional counter, and Geiger mirror counter are all gas field detector. The functional properties and application of the various types of ionization are largely dictated by their respective operating voltage dependent signals. You can see the ionization detector, the operating voltage 360, increasing the voltage you get to the proportional counter region 600 to 900, and increase further the voltage you get to the Geiger mirror counter. Response is stable, yes, for ionization chamber is stable, and Geiger counter is stable because an increase a little bit with the voltage will not affect the output signal. Sensitivity is low for ionization chamber. We can say intermediate for a proportional counter, and it's high sensitivity for Geiger counter. That's why we use it for contamination. Capable of energy discrimination, only proportional counter of the gas detector can discriminate between the energy. Application, dose calibrator ionization chamber here. It's research for the proportional counter, and it's used for contamination monitor, the Geiger counter. Any question about the gas field detector before we go to another type of detector? Scintillation detector is different type of detector now. Okay. So scintillation detectors. As indicated earlier, radiation from radioactive material interact with matter by causing ionization or excitation of atoms or molecules. When the ionized or excited products undergo excitation, de-excitation, energy is released. In scintillators, a portion of the deposited energy is released as visible light. Here will not, the de-excitation will not emit X-ray, will emit visible light inside the crystal. Amount of light to produce proportional to the energy deposited by the incident radiation. Okay. Increase the energy of the radiation, increase the number of light produced in the crystal. So, modern scintillators coupled to light sensor, or it could be photomultiplier tubes. This is the scintillator coupled to photomultiplier tube or photodiode and digital detector, plus electronics to collect, amplify, and quantify the signal. Scintillator used in scintillation detector, most commonly in a crystalline solid that scintillate because of characteristic of their crystal structure, mean that individual atom and molecules of these substances do not scintillate. They are scintillators only in a crystalline form. So it should, both in the specific arrangement, the crystalline, it's called crystalline to scintillate. The atom of this scintillator is not scintillating by itself, but we have to put in specific arrangement to get the scintillations. Here, there's the question, I think. Is this same as X-ray scintillators? I'm not sure. This is kind of, I'm not sure about this question, but it is, the principle is that there's the atoms of scintillator. We use a crystal, for example, and the atom of this crystal excited by the incident radiation. So the electron will be jumped from one energy state to another. During the de-excitation, the difference between the two states will be emitted as light instead of X-ray or whatever radiation emitted in X-ray apparatus. So this is the properties of the crystal that produce light. Okay, convert the energy, the incident radiation, to light. Okay, this answers your question. I'm not sure. Thank you. A scintillator is a primary characterized by intrinsic efficiency, decay time, and density and atomic number. Intrinsic efficiency, or called photon yield, is the amount of light produced per unit of absorbed energy. How much photon light will you produce per keV of incident radiation? Okay, this is the intrinsic efficiency. How many photon lights produced by keV of incident radiation. Decay time, the time in which emission of light takes place. Faster scintillators detectors can handle higher event rates on the detector and also reduce the dead time. The decay process should be very fast, excitation and de-excitation to be used in the imaging. Density and atomic number. For an efficient detector of gamma ray, a material with high density and high Z is required to absorb penetrating radiation. To stop radiation and detect it, we need high Z, high density material to stop radiation. Ideal scintillator properties. It should convert incident radiation energy into detectable light with high efficiency. This is the function of scintillator in general. Convert the incident radiation energy into detectable light with high efficiency. Light produced is linear proportional to deposited energy. Increasing the energy, incident radiation should increase the number of light photons produced in the crystal. It should be transparent to its own emission. The photon, the light photon produced in the crystal should not be reabsorbed again by the crystal. Should be transparent. The photon the light photon produced in the crystal should go to photomultiplier tube and interact and detected, not reabsorbed by the crystal itself again. So this is called transparent to its own emissions. The decay time should be short to avoid the time losses. It should have good optical quality. The optical quality should be very unique, not have many impurities inside it. Manufactured into practical size at reasonable cost also. However, no material simultaneously meets all these criteria, and the choice of particular scintillator is always a compromise among these and other factors. You could find high density scintillator, but a slow one. So you cannot find all these properties in one kind of crystal. The most commonly used scintillator for detectors in nuclear medicine is sodium iodide crystal doped with a small amount of thallium. It's called thallium doped sodium iodide detector. The thallium atoms here, the impurities, disperse in the crystal. The purpose of this thallium is to enhance the light output. Okay, this is the purpose of the thallium with the sodium iodide crystal, to increase the light photons, increase the light photon output. The advantage of thallium doped sodium iodide crystal used in the gamma camera mainly, it's high light output. Okay, the yield is high, and efficiency with thallium doping, of course, the efficiency is very high. The number of photon produced, the light photon produced per keV is high. Relatively inexpensive and easy to make. Reasonable decay time, about 230 nanoseconds. It has high atomic number and as well high density, and this gives high probability of photoelectric interaction. In imaging in general, we like photon interaction. We don't like Compton scattering. Compton scattering is reduce the quality of the image. We need photo interaction, and we know in the previous lectures discussed that photoelectric effect increase the probability is increased by increasing the Z material. That's why we need high density, high Z material to get more probability to get photoelectric effect and reduce the Compton scattering probable occurrence. The disadvantage of sodium iodide crystal, the sodium iodide crystal is quite fragile and easily fractured by mechanical or thermal stress, like rapid temperature change. Image show here large zigzag cracks with hot zigzag, with you see hot edges here. This was caused by impact on the crystal. Sodium iodide is hygroscopic also. So if the crystal is exposed to humid atmosphere, the crystal will eventually lose its transparency and become hydrated and reduce light transmission to the photomultiplier tube. Thus, hermetic sealing is required. We have to seal it just to prevent the humidity to enter the crystal detector. The crystal hydration is often seen as spots at any random place in image, as we see. This is the image of gamma camera, and we can see the spot. This is indication that this kind of detector is hydrated, and after some time, this crystal should be replaced. Okay, at higher energy, above 250 keV, Compton scattering dominates, and this is not good for PET application. So because PET application use 511 keV, so this kind of crystal cannot be used in PET scanner, it's used in gamma camera only. This table summarizes the properties of number of scintillators of interest for nuclear medicine application. So here we have the sodium iodide used in gamma camera, BGO, and LSO used in PET scanner. And we see the yield is very good here in the sodium iodide. Okay, but we have here, it is faster for LSO. That's why you use it in PET and time of flight PET. And we see the Z effective here is much better here. Why we have here high Z density material? Because we are dealing with high photon in PET, 511 keV. While in sodium iodide, we are dealing mainly with technetium and maximum iodine 131 with maximum 300. So we need high Z for PET application, little bit lower for gamma application. The second part of scintillation detector, so we talked about the scintillator, the purpose of the scintillator to convert the incident radiation to light photons. The second part of the detector is called photomultiplier tube, and this is the typical photomultiplier tube. Okay, and this is a typical photomultiplier tube used in gamma camera. Photomultiplier tube is coupled to the crystal in order to collect light photon and convert them into measurable electronic pulses. So this is the purpose of photomultiplier tube. So incident radiation interact with a crystal and produce light photon. These light photon detected by photomultiplier tube, the photomultiplier tube convert the light photon to electronics and pulses, converted from light photon to electron again to get the signal as an output signal. The outside of the crystal is coated with reflective material to promote internal reflection of light so that significant fraction of the light produced with the crystal is collected by BMT. So here is the crystal, and inside the crystal there is a reflection material just to enhance and to keep the light photon inside the crystal and increase the number of light photon detected by the PMT. So the light photon entering the PMT impact the photocathode, depositing their energy for approximately every 5 light photons hitting the photocathode inside the photomultiplier tube, 1 electron is produced. So we need 5 light photon interact with the photocathode to produce approximately 1. It's not fixed number, could be 7, 3, but approximately average, we need 5 light photon to produce 1 electron after interacting with the photocathode of photomultiplier tube. The electron is then accelerated toward the diode. These called diode inside the photomultiplier tube. Okay. A high-speed electron striking the diode surface ejects several secondary electrons from the first diode. Secondary electrons ejected from the first diode are attracted to the second diode at a 50 to 150 volt higher potential than the first diode. So between this diode and this diode, different potential. For example, here 50, here 150, here 250, 300. So there are different voltage just to attract electron from one diode to another diode. So the total electron multiplication factor is very large at the end after this amplification. The electron hit this one, amplify, this come here. So every time hit the diode, the amplification, there's amplification factor or multiplication process is repeated and repeated until we get the end of the PMT and we get the signal. And electron multiplication factor is very large. We said 6 to the power 10 for 10 stages of diodes. Okay. Any question about the detection incident photon? To scintillator, convert the energy to light photon. This light photon interact with the photocathode of the photomultiplier tube. We produce electron multiplication here, and we get the output signal. Okay. Application of scintillation detector in nuclear medicine. The first one is the thyroid probe, this machine here. The thyroid uptake probe is a crystal scintillation detector used to estimate the relative uptake of orally administered either iodine 123 and iodine 131 by the thyroid gland. A typical probe system employs a sodium iodide crystal coupled to the BMT, okay, and is surrounded by a cylindrical collimator to restrict the count to the area of interest. So this is one application of the scintillator detector in the thyroid uptake system, okay? The second application is the well counter. It is a shielded single crystal, okay, of sodium iodide with a well or hole here in one end of the crystal for the insertion of the sample. So all this one is the crystal, and inside, this is the crystal here, and we have hole or well to put the sample and read the activity or the number of counts of this sample. The sample is surrounded by the crystal so that only a small fraction of the radiation escape through the opening of the well. So that's why it has high efficiency, because most of the photons emitted by the sample will be detected by the detector surrounding the sample. The sodium iodide is used mainly exclusively to X-ray and gamma ray. It's not used to measure beta directly. Okay, so if you want to measure beta emitters, it cannot be measured by this one, because beta will be absorbed by the surface of the vial or whatever. But we can measure the bremsstrahlung produced by beta emission inside the sample. We know that beta emitters interact with high density material to produce bremsstrahlung. So this bremsstrahlung can be detected, and we can estimate the amount of dose for beta emitter. But usually we use the well counter for X-ray or gamma ray emitting. Well counter are used primarily for assay of radioactivity in a blood and urine sample, and also are used for wipe test and radiation safety monitoring, because it's very sensitive, can detect very, very few counts and give us the number of counts per sample. The third application is the gamma camera. We have separate presentation about the gamma camera, so I will not go into details now. So we go to the third type of detector, is the semiconductor detector. Any question before we proceed? Okay. The mechanism of radiation interaction in semiconductor detector is somewhat similar to the ion pair created in gas-filled detector. Semiconductor detectors normally are poor electrical conductor, okay? However, when they are ionized by ionizing radiation event, the electrical charge produced can be collected by an external applied voltage, as it is with gas-filled detector. So incident radiation produce ions. Here is called with semiconductor electron and hole. The hole here is the positive ion. Here there's the electron, and here is the positive ion, or called holes in semiconductor detector. The same principle. Radiation produce ion. These ions collected by electrodes. Okay. The most commonly used semiconductor detector material are silicon and germanium doped with small amount of lithium. Silicon detector are used primarily for detection charged particle, whereas germanium detector used in the gamma ray detection. The advantage of semiconductors, much higher density than gas-filled detector. They have much better stopping power and are much more efficient detector for X-ray and gamma ray. 3 to 5 electron volt of radiation energy is required to create ion pair. By comparison, this value of gases or air, approximately you need 34 electron volt to produce one ion pair. In semiconductor, you need only 3 to 5 electron volt to produce ion pair. So it's very efficient. Superior energy resolution, ability to differentiate between energy. So we can identify the isotope by using the semiconductor detector. It comes with a compact size, relatively fast timing characteristic, and no need for BMTs, because they directly convert the incident radiation to electrical signal. So there's no need with the PMT or other to convert to light, from light to signal, and so on. If from incident radiation, we get the output signal. So it is very fast one. And this is some properties of semiconductor, and you can see the density difference between the air and the germanium or silicon, the semiconductor detector. It has also high Z, and also the number of electron volt required to produce ion pair is 3 to here it's required about 34 electron volt just to produce one ion pair. This advantage of the semiconductor require cooling by liquid nitrogen, except there is one type of semiconductor now is called telluride, cadmium telluride detector, doesn't need cooling. So but in general required cooling, it has lower Z than sodium iodide detector. Okay, so it is lower efficiency than the scintillator detectors. They are available only in relatively small sizes. You cannot get big sizes of the semiconductor detector because it is very expensive. This is two applications of semiconductors. We have a portable high purity germanium spectrometer. This operates in pulse mode, and this is used to identify isotopes. If we have unknown isotopes, we use this kind of detector. We can identify the isotope by getting the spectrum of the energy spectrum of this kind of isotope. We have nitrogen cold silicon detector. It is mainly used in the cyclotron, okay, and also it is used to identify the isotopes in the radiopharmacy lab in the cyclotron. So to overcome the two major disadvantages, silicon and germanium detector, cadmium telluride and cadmium zinc telluride have been developed. They can be operated at room temperature, doesn't need any cooling, and they have high Z, so means better stopping efficiency. So the two problems of semiconductor detector is solved by found this kind of material, CZT. However, their energy resolution is poorer than silicon and germanium. Nothing's perfect. It still has a problem about energy resolution. But it's still significantly better than sodium iodide crystal, this kind of CZT detector. We can just compare the sodium iodide detector and CZT. So we have two isotopes acquired together. So consider we have gamma camera and we have two isotopes. We have technetium and we have iodine 123 is acquired simultaneously together. The energy of technetium 140, the energy of iodine 159, so it's close to each other. So with sodium iodide detector, okay, we cannot differentiate between the two peaks, hence simultaneous imaging not possible with this kind of detector for these two isotopes because almost like if used together. For the CZT detector, semiconductor detector, we can differentiate between the technetium-99, we have separate two beads, so it easily can differentiate these two beads, so this kind of image can be done with semiconductor detector. This is the means of energy resolution. This kind of a new camera available in the market is called CZT gamma camera. This is a dedicated cardiac camera, and this is very fast, efficient, give very high clarity of the image, is much better than sodium iodide detector. It's used mainly for a cardiac scan. It has semiconductor, so it's a great gamma camera for cardiac scan. If like center dedicated, they have dedicated cardiac cases, so this camera is recommended for that. It's not kind of advertisement. So I work in this kind of camera. It's really efficient camera for cardiac scan. So thank you. It was a long presentation, but sorry, this introduction about all the detectors in general and nuclear medicine detector in particularly. So next lecture will be about the gamma camera component on operation. And if you have any question, please let me know now.
Thank you, Mr. Mahmoud. It was really a wonderful one, and it's really important for them. And it's not easy, I know, to cover this aspect of nuclear medicine in one day, but thank you very much.
Thank you for you. It's a really tough time to cover everything in one day, many concepts, many things. But I try to do my best, inshallah.
Yeah, thank you. And I'm really sure that if they have any question, they can write it just in the chat. And at 1:30, inshallah, we'll be joining back.
Okay, thank you.
See you, guys. I'm going to close the recording now.